I'd like to introduce our speaker. It's my honor to introduce Dr. Klara Nahrstedt. Dr. Klara Nahrstedt is the Ralph and Catherine Fisher Professor in the Computer Science Department and Director of Coordinated Science Lab in the College of Engineering at the University of Illinois at Urbana-Champaign. Her research interests are directed toward tele-immersive systems, end-to-end quality of service and resource management in large-scale distributed systems and networks, and real-time security and privacy in cyber-physical systems such as power grid. She is the co-author of multimedia books, Multimedia Computing, Communications and Applications, published by Prentice Hall, and Multimedia Systems, published by Springer. She is the recipient of the IEEE Communications Society Leonard Abraham Award for Research Achievements, University Scholar, Humboldt Award, IEEE Computer Society Technical Achievement Award, ACM SIG-MM Technical Achievement Award, and the former chair of the ACM Special Interest Group in Multimedia. She was the general co-chair and TPC co-chair of many international conferences, including ACM Multimedia, IEEE PERCOM, IEEE IoT-DI, and others. Klara Nahrstedt received her diploma in math from Humboldt University, Berlin, Germany, in numerical analysis in 1985. In 1995, she received her PhD from University of Pennsylvania in the Department of Computer Science and Information Science. She's an ACM Fellow, IEEE Fellow, and member of the German National Academy of Sciences. Klara has been an inspiring figure for me as a young researcher. When I was doing my PhD, I was reading her papers and getting inspired. And I was fortunate to meet her later when I was teaching at Southern Illinois University, Carbondale, because she is also in Illinois. And she was very nice to write me a tenure and promotion letters. So please join me in welcoming Dr. Klara Nahrstedt.
Thank you, Kemal, for the very kind introduction. So I'm going to talk about some problems that I currently feel very strongly about, and some of the research that we are conducting in my laboratory, and hopefully sort of motivating further research in this area. And I do want to motivate the diversity of the Internet of Things systems that are coming, and particularly talk about IoT aging, that I think is a problem that will really be important for all of us. And then I want to talk a little bit about some new sensors and some new attacks that might be coming. And so we do need to explore the legacy sensors, IoT systems, but also the new systems towards security and privacy problems. So as we all know, the IoT systems are actually many, many different devices, sensors, actuators that are coming, and they are monitoring many, many different domains, our critical cyber infrastructures, and are then basically being collected into particular servers, being analyzed, and then provide further information to us for decision making or for further data collection. So the complexity of the IoT devices, I really would like you to think about it. It's not only, here is currently a thermometer, but really it's also this mobile phone, it's cars, it's instruments that we are currently monitoring things. So I think it's very, very broad and diverse. And so two problems I have run into over the last 5 years. The very first domain is that I started actually to work on power grid, and more recently, as I became a director of the Coordinated Science Lab, started to talk to materials research lab researchers as well as to micro nanotechnology device builders. These days, actually, I also am looking at oil and gas and healthcare and transportation. And one very interesting aspect is coming together. One is that these domains are buying new type of cyber-physical IoT devices, but also they have some older devices. So the important aspect is for those older devices, some of them are just not connected even to any of the servers or clouds, and people are actually collecting data with memory sticks. And that was just absolutely eye-opener to me, especially in the scientific world. In the oil and gas, actually, people are walking pipelines and collect sort of data from those sensors. And what is, at this point, really, very incredible is that through these memory sticks, you can bring viruses into those systems. Another sort of important aspect that is happening is that many of these devices are anticipated to be in the field for 10 to 20 years. Definitely it's true for power grid, but I actually, as I was working with these instruments, for example, people really are buying them for 20 years. And that actually means that a lot of the application software, maybe they give you guarantee for that particular instrument or for that particular IoT device for 5 years. But after that, basically they said, goodbye, you buy a new instrument. If that particular new IoT device is a couple of $100,000 or $1 million, you are not having always the means to replace that. And so these application software then basically has to run on old operating systems because this application is not updated, and so you are basically not patching your operating systems, and so very often then either you disconnect your IoT device from the network, or you basically are risking being attacked. And so we are actually seeing major IoT device age being as an issue, because in many, many domains of these calibers, it's just too expensive to replace these IoT devices. And so the big question for me actually became is how do we start to think about these trustworthy cyber infrastructures for IoT devices where you have old and new type of devices. The second problem actually that is being on the table, I think, is that many new devices are coming or improved devices are coming. And I think that is the best example is actually in your mobile phones, right? That these mobile phones are starting to come up with many new sensors, or the audio sensors, the camera sensors, all of them are just getting more megapixels and better quality of audio. And also, of course, what is helping is that as these sensors are getting better and better, new algorithms are being developed, machine learning, hybrid learning. I mean, it's really amazing what's happening in that space. And of course, also your mobile phones are more and more actually major supercomputers. And so the big question for us at this point is what kind of new security problems are these new devices, IoT sensors representing? What kind of privacy leakage could there be? And so those are sort of questions that we are asking. So I'm going to talk about these two spaces, two problems. In the first space, I'm going to talk about the aging of the legacy IoT and give you actually an example from these scientific instruments that we are working on. And then we have been and are working through National Science Foundation on the system for seed bracelet, which is trying to get us closer to at least addressing some aspects of the aging. So so there are sort of really interesting aspects from the scientific instrument spaces that basically more and more these microscopes. These are, just to give you a feel for, microscopes are $1 million to $10 million instruments that can have up to 300 sensors. And the sensors can be imaging, can be temperature, pressure, humidity, I mean, you name it. Basically, these particular instruments are connected, and basically have next to them a computer that will then collect all of these sensors, and then the scientific application software needs to process the particular sort of data and sort of provide it to the scientists. One important aspect actually is that this particular computer will actually will have scientific software that many of the functions are embedded in the operating system. So in some way, when an operating systems get upgraded, it is very important that Carl Zeiss, General Electrics, or whatever sort of companies are developing microscopes as sort of these IoT devices, they need to upgrade basically their software as the operating system gets upgraded. So a lot of these instruments are generating tremendous amount of big data, and they need to be captured, uploaded, curated, analyzed, so a lot of things. And so I was actually observing what these scientists are actually doing with these microscopes as end devices, as IoT devices, and they basically are putting together, for example, material scientists put together chemicals, then put them in the petri dish, put them onto the microscope, and then basically are collecting the data from this particular computer, converted into some sort of formats, and then basically you are sort of ending up with a lot of heterogeneous type of data. And the next thing is they put in the memory stick and sneakernet it to a local computer in their office. And so that was actually, then they basically in their office analyzed the data, realized, oh my God, it's all garbage, let's throw it away, all the data, let's go back to the lab and do it again. What National Academy came up with was that basically between the time you are inventing new materials and you are using that particular material in the next chip, right? Sometimes it's 20 years. And the big problem is actually that this collection of data, analysis of data, is part of the problem, and so on. So there is a lot of sort of very interesting sort of spaces to innovate. But of course, the big problem is now that from these microscopes collecting a lot of the sensors, a lot of the IoT type of data, is that these are long-tail scientific data, right? They are small data, right? Temperature is a small data, humidity is a small, and then they basically all get sort of aggregated. And very often when you are looking at scientific world, is they usually deal with these astronomy type of homogeneous, large-scale telescope type of data. They know how to sort of collect them and then process them. But big problem is that these IoT data, which has really more long-tail data, it's much, much less cyber infrastructures are sort of available. And so basically a lot of these data scientific that don't even appear in the published data, published spaces. So we have been looking at this whole process, and we definitely identified that memory sticks are a major security risk, and so we really need to get scientists away from these approaches of collection of data. Another really important aspect is the access of data, and they really are very, very hesitant when even they are sharing somewhere the data, who can access the data. One of the important issues and differences is actually that for you and me, the major result is algorithms. Right? We basically are living off that. The data is less make it or break it in your world. For the sciences, like material scientists, biologists, chemists, and so on, the data is the research, what they collect from these IoT sort of type of devices. And so access to data, having time-driven data access, having different sort of groups access over the time. So for example, they really would like to have access first 3 months, only the researcher who actually collected the data from the microscope. Maybe after 3 or 4 months, then their advisor could actually look at the data. Then basically they open it maybe to their bigger group after 6 months, and then they publish it maybe after a year, and so on. So very interesting sort of different pattern of access to the data. And as I mentioned, these scientific instruments are becoming very quickly obsolete. So for example, as you know, Windows 7 is going to be stopped patching next summer. We are all moving to Windows 10. In our material research lab, 90% of microscopes are running now Windows 7, Windows XP, Windows NT. There is actually 1 or 2 Windows 2000. But we basically decided not to even address that because it's really difficult. So there is basically the problem that these scientific applications are obsolete because the contract expired, and many of these companies are not going to update it. And so we need to help them, I think. So the challenges are from this particular space is really the heterogeneous scientific data management processing, really complex analysis. Very often when you have this kind of complex IoT systems, the scientists want to run workflow analysis of analyze humidity over the particular day that I am running my materials and chemical processes, analyze the images that I have been taking over the 1 hour. So there are multiple sort of processing, extract metadata, create histories, and so on. So really complex data analysis workflows. And of course, the big issue for us as computer scientists or computer engineers is to create cyber infrastructure that is trusted and provides actually very short time to the interpretation and insights. And so we want to actually do real-time, sort of secure data capture, acquisition, access control, and of course, analysis. So I want to talk about 3 sort of interesting problems and solutions that led actually to this particular secure edge-augmented data acquisition. And that is the microservice execution and then feedback shortly, and then the security, how we addressed. So this is currently our sort of approach. You basically have private clouds, and then you have these microscopes as IoT devices that get over locally on our campus network connected to this particular private cloud. One interesting aspect was another thing working with scientists, and that is I actually asked them, why don't you just go to Amazon? Why don't you go to Google? And the answer is, I don't trust them. Basically, because the data is so valuable for many of them, they feel that if it's close to them, if it's somewhere on the campus, that and has certain securities that, so that's actually what was very interesting to us. But my feeling is that many of these companies are going to be following with higher security, higher sort of capabilities of satisfying these scientists. They basically feel that they will put onto Amazon, onto Google, on any other sort of their data when the data is published. That's their condition. But in between, they want to have it closed. So in terms of the long tail scientific data processing, we felt because there are so many small tasks that these scientists want to do over their data as the data gets collected from the microscope, connected, so it's get uploaded into the cloud, that you basically are working with these data analysis workflows, and it's not batch, it's basically real-time sort of type of processing, so a lot of the previous solutions didn't quite work, and we felt that the microservice concept via Dockers is a really nice solution, where basically you have a microservice where different clients actually subscribe to, for example, an extraction task. And you basically have multiple tasks, multiple users that currently want to run extraction or do humidity data analysis. and there is basically a task queue that this particular task will wait. And you can have multiple tasks. On your images, you want to look at currently the color histogram. That might be basically the task A. You could basically look at do a line detection. That could be another one, and there could be multiple users that basically have demand for task A, for task B, because you have multiple IoT devices that are currently providing the data into the cloud and want to run these workflows. So you have data, you have task dependencies and you want to actually have a flexible workload compositions, and that basically what the microservices will allow us. And so the architecture actually cloud for these IoT type of devices with many, many different sensor data, with many different workflows, we basically created. This is actually the cloud architecture where you have these different tasks sort of from the workflow, and you have a task dependency servers where every user can actually upload its particular task dependency it wants to do on all of the multi-sensor type of data, and of course then you can curate and upload and look at it. So you basically have data here basically where in the workstations you can define what is the current task dependency graph, gets stored here, and then as the data will come, you basically have a broker that will basically upload what kind of task dependency tasks you need to run. Here is, for example, graph A, 2, and B, and then end. And then basically you go to this publish-subscribe type of system where the request basically gets processed. There's, of course, database which has the data, and then different tasks basically driven by the task graph will be processed one by one, and will be basically coordinated so that you can get it properly processed. So this is basically the main sort of service that we provide now for the IoT, and you basically get a result from the curation. Now, we also, of course, because you have many different users, many different instruments, you are having a lot of tasks. There is a lot of heterogeneity in the data formats, workflow structures, usage patterns. So we basically also have been working on the control optimization, learning capabilities over the system data for resource adaptation. That was actually a very sort of fun project to actually, in terms of these complex IoT systems, to monitor them, particularly monitor microservices, and then actually do major adaptation on the level of, on the level of the microservices. And for the microservices, we are actually trying to utilize as many open source solutions as possible and basically integrate them. So as you can see, our cloud basically will have the Kubernetes, then basically using RabbitMQ as the publish subscribe for the Dockers. Now basically we are moving to the Docker Swarm. And then of course there is a lot of tools for microservice monitoring, and we are using actually machine learning to learn about the state of these microservices. So for many, many different work task graphs, we wanted to see basically how close are we actually able to mimic and adapt resource allocation for these kind of IoT sort of system, very diverse traffic. As you can see, this is materials data flows, and this is actually the LIGO workflows, right, from the physics. They have actually very, very different over various sort of data. And we actually felt that we are actually coming very close, estimating actually how many resources we need to allocate for our microservices and their corresponding workflow tasks. As you can see on the x-axis is the arrival time, this is the current sort of processing time, and this is currently our estimation how many the microservices can be allowed into the system, and particularly also number of users per task we can allocate in order not everybody to wait for a long, long time, right? So there's certain admission control. So in this particular architecture, as a cloud architecture for these IoT multi-sensory type of instruments, really was a precursor for us to address then some of the security issues. And the security issues were that we connected the new instruments with all of their multiple sensors, but some of these older microscopes were all offline, and so we couldn't connect them. The IT team actually said disable them because of Windows XP, Windows NT. And so for us, two important issues started to come up when we started to look at the older microscopes and sensors. One is performance mismatch. Some of these operating systems actually are still on a 10 megabit per second network. And our cloud basically would run on 10 gig, right? Sort of network, campus network. So you started to have sort of a TCP timeout problems. And the second big issue, much more important, was really the security. For example, the XP nodes and NT basically didn't have HTTPS, didn't have any security, and we actually wanted sort of to employ the web solution. There is a certain authentication, but of course, you would send everything plain text between the old operating systems and computer on the microscope to your cloud. So we have been seeing hardware aging, and this is not only hardware aging in terms of the microscope, that's an optics, and the optics can survive 20 years, but the computer hardware is basically was aging. Software aging, already older apps, and so a lot of software vulnerability, no HTTPS, no proper authentication and access control. So we basically are now exploring and explored actually the edge computing technology, where basically this is currently our edge computer that is on a local area network to these older instruments, and this particular edge device then has the interfaces. It has a very strict interface to the older equipment to check at which speed currently you are sending so that it doesn't times out, and then basically it serves and transmits the data to the cloud at higher speeds, so it does sort of the traffic shaping and offloading. And from the security point of view, it really looks at all kinds of security. It looks at the user authentication, registration, instrument registration, data encryption, sort of underlying, and also firewall protection. So we are currently, so you can see here, this is actually our cloud, and we actually also are looking at the edge device in a very similar sort of Docker type of architecture to actually have the tasks. And one of the reasons is actually that we are also anticipating that some of these tasks might be offloaded from the cloud closer to the edge device and to start to do processing of some of the images. For example, our MRL just bought sort of $4 million microscope that is producing 4K images at quite high rate, terabytes of data, and they want to basically move it. And so we are at this point talking to them to actually put some of the tasks also into the edge device before we start to sort of move it across to the cloud. So you basically are having the architecture, which is basically the execution architecture of the publish, subscribe, and the task dependency service, and then you have the monitoring and the adaptation, how many microservices can you accept, but then basically you are having the space here. We are sort of replicating the space here also for control of all of these tasks and connectivity to the particular cloud. Of course, there is a security for the campus network and very, very tight control for these particular old devices. So if you sort of think about authentication, remember, all of these devices are currently unprotected. So in some way between the old device and the edge device, which is closer on the local area network, there is unprotected sort of plain text password, but then basically at the edge we are actually doing Shibboleth authentication as well as providing user authentication, that do you have the right to the cloud, as well as instruments. There are a couple of sort of authentications. For example, are you scheduled to be on this particular instrument? These instruments, as you can imagine, for $10 million, sensors are being scheduled, shared, and so we basically check for many, many things. But here also MAC layer, IP level is going to get checked so that because only devices from the particular device, all device can be moved and relayed from the edge basically to the cloud. And so you also check if this particular reservation has been provided. And then you basically are moving the data. We, at this point, from these old devices, only allow the uploading so that we can actually control just one-way data and hoping basically and checking that nothing gets further sort of into these old devices. And the reason is that if that particular device gets infected, basically there is a damage that cannot be repaired. So here basically the processing then goes very similar as it went through the cloud, that particular for the uploader control plane gets an information from the task dependency graph. Can I basically currently schedule it locally in my task? If yes, then basically that's what I do. I put it into the task Docker to actually run that particular task on the edge device and then move the result actually to the particular cloud Docker, which runs my task B. And I am done. And again, we are at this point doing central adaptation, monitoring how the microservices are using resources at the edge device and at the cloud to actually estimate A, what's your waiting time, and B, basically how many microservice, how many users per microservice can be admit. And that particular estimation actually, again, works well for the cloud microservice D and for the edge device microservice C on the cloudlet. So to conclude this particular part on the aging is that we basically have to, I think, address the aging of the IoT devices. And one of the solutions, I think, will be sort of really creating these very sort of robust edge devices that can be constantly upgraded. And the second thing is really sort of through the secure network configuration. So we are actually having this bracelet server now in front of all of these old devices, the hardened operating system and running sort of Docker Compose. And the network configuration is also very important. So these are currently all the old devices that get basically connected to the bracelet server. It basically goes traffic, and then the traffic goes back to the particular cloud, and it gets very, very carefully sort of checked. Our switches do MAC checking, that it basically comes only from those devices that it's supposed to be. So the second part of the discussion that I would like to bring forward is some of these sort of enhanced, newer type of IoT devices, and particularly talking about audio-based IoT privacy attack. And here, a lot of people have been using audio and studying audio for attacks. We have been sort of studying, particularly people have been listening to keyboards and trying to infer if there is what kind of text people are writing. So one interesting sort of aspect for us is that in particular in the healthcare industry, there is no typing. You don't type your personal information, but very often you come and basically you have to fill out your forms. And so we actually have been asked basically, can one use now these improved phones, and particularly the improved audio devices, to actually listen to the handwriting and find out what is currently happening. What is the person writing? So the sound of the handwriting, can it leak actually a personal information, in particular medical information? And we basically starting to study this because the rapid evolution of these mobile terminals really compounds the danger of audio-based eavesdropping. People actually put their mobile phone next to you as you are filling it out, and they could, we were curious if one can actually organize that kind of attack. So to what degree can an attacker eavesdrop on our handwriting? That was sort of really the big question, and particularly eavesdropping on the nearby devices. So if one think about sort of as an attacker, one thing is that you don't have a direct contact with the victim. You basically just stand next to it. You don't have any data from the particular victim, and there is no constraint on writing location. And so the solutions, very briefly, I want to talk about is the writing hacker. So the writing hacker is a, the writing hacker is audio-based eavesdropping, and the major assumption is that people actually do print-style handwriting. That was sort of one of the important sort of goals for us. And that is usually a reasonable assumption, because when you write these forms, very often you get asked, do print letters, printed letters. So we basically started to look at these, the attack method. The attack method would be that the attacker keeps her mobile device sort of touching the desk and to record the victim's handwriting sound. And the attacker basically collects the training data from sort of other people. So you could actually have other people outside of the medical environment where you actually already have certain training data, but from other people. And then the training data sets basically include sound segments of these characters, A to Z, for example. So, and then the writing hacker comes to a medical establishment and starts to listen and basically infers based on some of the method that I will talk about, can basically estimate the handwriting of the victim. So the architecture is, and the algorithms inside of these individual blocks are in the paper, so please, I would like to refer to that, but I just want to really get the high level of this particular approach to sort of show the importance of this privacy leakage. So the first step that the attacker's tool basically could do is do input detector. You are listening actually on the sound waves, and you receive the sound streams, and you basically can, because the sound is now so detailed, so refined from these mobile phones, that you can actually extract the sound fragments and number of strokes for each letter. So for example, if you write B, letter B, you have a 1 stroke and then second stroke, 2 strokes, and so we basically are then taking the, detecting the strokes and then basically classify them into certain clusters. There is a letter that has, for example, V. It's just a 1 stroke, right? So in one way you are going, but some of the letters need 2 strokes, some of them need 3 strokes. And so you could already cluster the letters A to Z in how many strokes you need. And this particular first step will allow you to do that and can actually start to sort of detect some letters, or at least group of letters. And then in the second step, you are basically having a dictionary. So for example, if you are in a medical environment, you could actually have already certain medical names of diseases that you anticipate people will write in. And so you can basically start to do a dictionary filter, because from the first step, you actually get letters. You might start to build words out of those, and this particular dictionary filter actually can sort of give you certain filtering, which words might make sense, which might not make sense. And so the particular dictionary filter narrows the candidate words according to the stroke information. And then in the third stage, this word recognizer recognizes each word according to the features of the sound fragment, and then basically the candidate list using basically the dictionary and then the training data. So if you start to look at some of the databases, if you, for example, have top 2,000 commonly used daily words, 5,000, or for example, there are available now these medical related words, we basically have been experimenting with these particular databases in our system, and the evaluation is showing us that if you don't know with our system, you basically get around 60, 70 accuracy problem of recognition what you are writing onto that paper. So with the full biome, this is actually a quality of recognition if you would have the actual victim's data. But of course, we assume that we don't have. If you have actually the victim's writing or users writing training data, you can then very quickly sort of recognize what the writer is writing. And this actually is a very interesting other sort of use case. Another sort of use case that comes from the healthcare was sepsis. Hospitals actually are trying not to use keyboards because of the transmission of all kinds of diseases via keyboards among nurses. And so they actually have been looking at different input methods of the medical information. And so again, handwriting and then having audio helping them and transmitting the data into the database was one approach. But we have been actually looking much more at the privacy leakage and really sort of pointing out the possible issues. And this is actually on the x-axis, we have a size of the data dictionary database, and this is again the accuracy. And as you can see, the more closer you have more words, more closer to the domain where the attacker is actually listening, you can have a much, much higher accuracy. So there are a couple of major issues at this point that we are keeping sort of investigating. One is, how far away you have to be from the particular victim. So this is currently distance between the smartphone and the handwriting in terms of centimeters, 220 centimeters. And again, the accuracy detection, what kind of desk it is to actually, when people are writing, if you have currently a wooden desk or plastic desk, as you can see, the plastic desk doesn't carry as much the sound. It's again sort of around the 50-60% accuracy the attacker could actually listen to what you are writing. So to conclude my presentation from the privacy perspective, I do want to sort of point out that many of the new sensors that we are getting are improved or are new, and so new possibilities of security attacks or privacy leakage in this particular case are possible with all of the computing capabilities that these mobile phones have. For example, in the mobile space, I find that very sort of possibility can happen that you don't even need training data or writing locations. People actually could be listening. And I am sure there will be many new sensors that we need to again look at. To conclude, I think having all of these new IoT sensors in many, many domains The good thing is we are getting more contextual information. Now that you are here in Chicago, probably you might have heard about the area of things. Many of the intersections in Chicago are going to have actually boxes that are going to have multiple sensors, and these multiple sensors actually are actually already monitoring the quality of air, the transportation density, and so on. So the reason is actually really to get a better information to the public about traffic and about the various environmental aspects, chemical sensors and so on. So better situational awareness for many of the cyber infrastructures, critical cyber infrastructure, water, waste management, and so on. I think that is sort of much, much better even as we have more and more sensors, and better decision-making control can happen. But my sort of goal is actually to really understand the problems of privacy leakage, concerned that a lot of the information can be abused without proper protection policies. There could be actually increased potential physical attacks, as people might have more information about me, and therefore do some bad things. And it can also lead to some mixed, wrong conclusion decision-making, since a lot of the data still is noisy, augmented data. Also, we have now the adversarial machine learning, right? A lot of people are researching. So I feel that this is definitely an important domain to study as we are moving towards future IoT system. And this all has been possible with a lot of collaborators and funding. Thank you.
Thank you very much. So we have some time for questions. Questions?
Thank you, Klara. It was very nice. I have a question. So often when you're working with machine learning techniques, we see results related to accuracy, which give you the percentage of the times you find the right answer. But often you don't really look at the false positives. And you don't really know when you have accuracy what happens with the times you went wrong. Was it wrong because you couldn't identify a word? Or was it wrong because you said, I learned cancer, it was cold? And my question is, how can you capture that? Because I think it's important as well that if an eavesdropper understands it's cancer and it divulgates this information, it may have impact on you while it's wrong.
Right. So what you are sort of asking is that if there are noisy data, right,
yes,
that I'm currently...
whether the results you trust it or not, and how you know that you trust the result.
Right. So so there are definitely issues, and for example, we have been testing some of the microphones, sort of mobile phones, when you have servers, for example, are sort of having the white noise. We are not capturing it at this point, right? So this is a very good point that to in some way capturing what environment, what sort of other noise level would be there, because that actually interferes. I mean, one of the big issues for us that we need to further study is the difference between as people are writing differently, right? And how long they stay with one particular strokes, or do they have differentiators? That's actually why, for example, the number of testers was still quite small, and we have been finding that people who have a very nice sort of writing would be much clearer in terms of their sound differentiation. But of course, when you are in a medical office, people are talking, right, and so on. So there's a lot of things that is picking up, and we haven't captured that noise level that could actually contribute that. We are trying to remove the white noise, but talking, some of these other impacts, we haven't done that. But those are definitely very good directions to go.
Another question here.
Thank you very much for this inspiring talk. I have a question concerning security and privacy in software maintenance in the constrained IoT. You have, in this case, you have billions of devices, no user interfaces, quite a number of stakeholders, data operators, network operators, device operators, manufacturers, and so on and so forth. And it is quite difficult to devise a secure management of software. Do you have any insights on that?
So I can talk through the software environments that at this point I work with respect to the material scientists or the semiconductor scientists that are using some of those instruments. And there is sort of an IT organization that works with the operational group to do provide not sort of the physical security, but also certain policies, certain guidelines how sort of the software has to be protected. Now, so in that sense, at least some of the back-end services are driven by university policies. What can be put in, what can be done. Now, we are facing with a very interesting other problem. The IT organization that works with the OT organization is checking when the microscope gets purchased, are there certain guarantees how the software gets so there is a whole chain of processes. The biggest issue at this point, we are very worried. I talked about the workflows, right? Sort of dependency tasks. And many of the users would like to write their own software and download it into these clouds, right? To write and so on. These users are power engineers, are material scientists. They never studied computer science. And so there we are at this point talking about some kind of back-end, front-end. We are not quite sure where to put it in. That as these new software, right, the same as Google Apps, some kind of check has to happen, either verification. This is at this point for us the biggest challenge of the software as it grows. For example, in these IoT sort of spaces, that we have people who have not been trained. And so I find in the power grid, I hear that, how do we create certain pipeline on verification, formal methods, standards, what can be put into the system and who can put it into the system. So that's an insight at this point I have, and problems that we are facing.
Klara, great talk. Just to follow up on what you said, to check actually what you put into the system, do you think there is also an opportunity to check what's going on in the system? Because if you observe what the system does and how it behaves, you might be able to catch things that you have not been able to identify when they went into the system.
Right. And that's actually where, I find the, I want to go back to that I'm hoping that many of the systems will have the capabilities of, maybe I can keep this up, that particular top layer, these adaptation layer and monitoring layer, also for security, especially now where these cloud systems with Dockers allow users to upload anything, right? I mean, where the scientists are going or the people are going work with IoT. Oh, I can write an app and then upload it and then run it, right? we have to then have in these underlying middleware layers strong monitoring and adaptation so that work in progress to check, right? If you are taking too long, you get preempted, right? And or get thrown out to basically check on that because, but what currently concerns us and if anybody has really good suggestions on that, is that a lot of people who are going to write software for the IoT systems and networks are not computer scientists, right? So are not sort of aware of security, of the proper software engineering. We are concerned. So there are tools now, for example, Jupyter Notebook, that the scientists are very excited about because they can actually write all kinds of apps. They have libraries, right? And bring libraries from wherever. And these libraries can have viruses, they can have malware, and nobody's checking. And they are, even we have Dockers, right? And sort of you feel like, okay, there is a little bit protection, but the Dockers are microservices, they are not virtual machines. And so suddenly you can start to infect your cloud infrastructure. But everybody's going towards microservices because of the lightweightness and performance issues and so on. So I very much agree with you. I think that these layers, the monitoring, the adaptation towards security will be very important in the microservice area.
Okay, thank you very much. Maybe one final question? I was just wondering if you deployed those edge devices in the materials lab, and
yes, we did.
Who is in charge of the management?
Yeah, and this is again, the edge devices is the IT organization of the College of Engineering and of the labs. So it's not the students, it's not a staff, it's security officers, and actually the networks that have been configured to put these older devices onto connecting to the edge device have been again network security experts, because you do need to configure very carefully whitelists on those particular edge devices, and on the network LAN switches, you have to check for IP addresses that it basically came about. And also we are at this point creating an interface for the security experts to the edge device to check on, log everything that is happening, and regularly sort of uploading and then checking on that. So BRO, which people know, we are checking on the traffic, seeing basically are there some strange behaviors happening. So these security edge devices, I think it's going to be one of the applications for edge devices that I think it's going to be very necessary.
Great, thank you. Let's thank the speaker again, and we have a small token of appreciation. This is your certificate.
Thank you so much.